and under no circumstance this IP must be compromised, stolen, or be tampered with in general. Now, typically in such systems, this information is stored into non-volatile memories or NVMs. And in order to protect it against malicious users that want to simply access it, we use traditionally encryption, while on the other hand, that we want to protect also the system from potential faults affecting the content of the memory, we use error correction codes, which can assist with detection and correction of in specific cases. Now, the goal of ours in this work is to evaluate whether it may be possible to enhance the reliability of a system that is currently executing a machine learning application by exploiting the potentially pre-existing encryption mechanisms that are used to protect the IP, which is the weights. In other words, whether we can achieve the reliability through security. Now, for example, some scenarios of attacks on intellectual property could be that someone that is interested to check which is this information that is responsible for the case of a classifier network would like to extract this information, extract the weights of the network, or in other cases, we could have something that can be more dangerous. For example, someone to be clever enough to play with specific values inside the memory, to have, let's say, some extra knowledge about the technology. And this can have catastrophic consequences, not only for the user, but for the surrounding environment as well. For example, in the case that this could be a system that is on an autonomous vehicle, the consequences could be catastrophic. Now, in the proposed abstract model that we have here, we interlay a decryption module in between the processor that is executing this application and the memory that stores the data, which is the weights of the network. And every time these weights have to be loaded into the application, then the decryption module decrypts and passes them to the processor. In that case, it is possible, if a fault is present in the content, to either have a detection through the decryption mechanism in certain cases, as we will see in a few slides, or in the case that the data, like in the case of the machine learning application, are floating point numbers, we could have the decryption process to augment the fault effect and generate some special condition like a not a number case, a non-value, that may allow the software, if the software is the appropriate one, to detect the fault. Now, on the fault model that we used, we rely on the transient faults. Specifically, we use the single event upset model and the multiple bit upset. The multiplicities are 1 for the single event upset, of course, and then for the multiple bit upset, we use the fault multiplicities of 10, 20, 50, 100, 200, and 500. Also, we assume that the fault affects the already encrypted memory content. And the potential outcomes are based on the fault effects. We could have a safe or a silent fault. This means that the fault does not reach the network outputs, and thus the classification does not change. So it's the similar one with the fault-free network. We have the dangerous scenario, which is the silent data corruption. The fault reaches the outputs of the network, but it is not detected, and thus it changes the classification of the network. And lastly, we have the desired outcome, the detected faults. Regarding the encryption mechanism that we use the traditional advanced encryption standard, or AES, of key length of 128 bits. And in that case, we use different modes of operation. On the one hand, we have the counter mode and the output feedback mode. And on the other hand, we have the cipher block chaining, the cipher feedback, and the propagating cipher block chaining configurations. Now, these are divided into the non-propagating, as we call them, configuration, and the propagating configuration. The non-propagating ciphers, or modes of operation, do not amplify the fault effect. Namely, one fault, one bit flip, let's say in the encrypted memory content, is mapped to one bit flip in the plain text after the decryption. While in the other case, when we have the block modes of operation, we have one bit flip to correspond to multiple bit flips in the plain text. Now, these modes of operation are also used with and without padding. Regarding the machine learning application we targeted, this is the convolutional neural network LeNet5, which was trained on the MNIST dataset of handwritten digits. And just to have an idea of the size of the trainable parameters of the network, we speak about 210 million approximately bits. Now, moving on to the experimental setup, the first thing that we wish to get is the fault-free classification results. So we simply load the weights inside the network and we launch the classification of the test set. And then we store these golden results to be used as a reference. For the sake of completeness, I mentioned here that the description of the network and the implementation was done in the open source darknet suite. And then we move to the fault injection campaigns that we launch. First, we have the weights. And for every fault model that we used, for every mode of operation of the AES cipher that we used, and also in the cases that we have and we don't have padding, we do the following. At first, we encrypt the weights, and then we inject a fault of a given multiplicity. Then, during the decryption, if padding is used, we may have an instant detection of the fault if and only if the fault has affected one or more bits of the padding segment. Now, if this is the case, and padding, of course, as I mentioned before, is used, we can have a detection of the fault here. If this is not the case, then the corrupted now weights are being loaded into the network, the test set begins the classification, and then we compare with the previously extracted golden results. If the two match, then we speak about a silent fault. If they don't, we have the silent data corruption. And if the software raised an exception, which means that the current classification stopped due to the not a number case being generated, then we have once again a detected fault. Now let's move to the results. First, we have the single event upset model and the no padding scenario. Now, as a reference, we use the no encryption scenario here, and these are the numbers. For example, the highest, as expected, the highest amount of faults belong to the safe category. Then we have few cases of silent data corruption and no detected faults. If we check, if compare with the non-propagating configurations, counter and OFB, then we can see that the results are pretty similar. Not significant gain comes to terms of faults being detected here as well. And when we compare with the propagating configurations, once again, what we expect is to see an augmented percentage of silent data corruptions as it happens here, simply because one bit flip in a single event upset, we have a fault with a multiplicity of 1, will corrupt the whole, at least the whole block, at least 128 bits, which means that the probability of having an SDC increases as well. What is interesting here is the PCBC. For the PCBC, we can see that we have a very big increase on the detected faults. And this is due to the nature of this block of operation. One bit flip, when decrypted, will propagate towards every following block downstream. And thus, it has a very high probability of, let's say, generating a none condition. Now, if we compare with the padding scenario, we can see that the PCBC behaves even better. No significant gain comes once again for the other ciphers and reaches 99.9% of detected faults. This happens because almost every time the fault will propagate and hit will corrupt the padding bytes that are added during encryption. And during decryption, this will be detected, and thus we will understand that we have an erroneous misbehavior of the system. Moving on to the multiple bit upset, we begin with the no encryption as a reference, and then the counter and the output feedback mode. We can see that they pretty much are overlapping. They are showcasing similar behaviors. Then the CBC and CFD modes have, let's say, proportional relationship with the injected fault multiplicity when it comes to faults being detected. As the fault multiplicity increases, so does the fault detection rates. And then we have the PCBC that behaves very well. It has very high fault detection rates due to the fact that it affects every trail following, let's say, block of weights. But in the case of the multiplicity reaching 200 and 500, we can see that we have a slight decrease. Then we go to the padding scenario, which the results are similar as before for the streams, the non-propagating configurations. For the propagating configuration, the two, we have the similar behavior, and PCBC almost 100% of the times detects the faults. So with that said, it is true to say that if we carefully choose the encryption and decryption mechanism to be employed, we can possibly have some remarkable fault detection capabilities. This is not to say that, look, we do not need error correction codes anymore. No, this is not the case at all. But a potential combination of these two methods could potentially help us to achieve better results in terms of detecting and also correcting faults with lower costs, because these things do not come free. They need extra hardware. Of course, the error correction codes are based on the redundancy, so they cost. It's not a negligible cost, but if we carefully mix those two, maybe we can achieve better results in the future. And with that said, that would be all from my presentation. Thank you very much.